Hi. So the next part of the section is just talking about outliers. And outliers are just values of your data that are outside the scope of your data. And sometimes they're included by chance, by sampling variability. And so we just want to make sure if we want an honest reflection of our data that we want to stay within the scope of our data. And we can't just look at data pieces and say, no, that doesn't belong there. That's cheating essentially to your data. So mathematically, there is a method in which we can find these data points, and that's called outliers and determining the lower and upper fences. So let's go ahead and do that for the model weights that we just did above. So here, to check for outliers using quartiles, we can go ahead and determine essentially the 5-number summary. And after you identify the 5-number summary, we can go ahead and compute the IQR. And when we identify the IQR, then we can find the fences easily and then determine and look at our data and see if there are any values outside the scope of our data. So let's go ahead and determine if there are any outliers to our previous example with the model weights, and determine the lower fences. So let's go ahead and do that. So in step 1, we went ahead and found those out, the Q1 and Q3. If we go up just a little bit, we can see that here is our 5-number summary, and then here's the IQR that we also found. So we can easily see that Q1 is equal to 91.5 and Q3 is equal to 115. So step 2 is computing the IQR. And we did the IQR in the previous problem and we found it to be 23.5. And essentially recall that these are pounds of weight of models from that model agency, right? And so step 3 is determining the fences. So of course we're going to have fences, and essentially what they are is like the bounds. We're saying like if anything is outside of the lower fence, like over here, it's an outlier. And if anything outside this upper fence here, that's an outlier. So anything else, here's the fences. We're saying let all the data, make sure all the data is within the fences. It's like letting the sheep out of the gates, like we're just keep them all here, So let's go ahead and determine the fences. So the lower fence is just going to be Q1 minus 1.5 the IQR. And the upper fence is going to be Q3 plus 1.5 the IQR. So it would just be the lower fence 91.5 minus 1.5, 23.5. The upper fence would be Q3, which is 115, and you would just add 1.5 times the IQR. Okay, so if we went ahead and put that in our calculator, I would have 91.5 minus 1.5 times our IQR, which is 23.5. And essentially, I would do the same exact formula, but adding with the Q3 and then, but the same 1.5, 23.5. So 56.5 is our lower fence, and 150.25 is our upper fence. Okay. Oh. Okay, so the next step would be is to go back to our data and see if there are any that lie outside of this. So here are the fences. So if I go here and look where 56.25 lies within my 5-number summary, well, 56.25 lies way out here And 150.25 lies way out here. So notice that the fences are outside of all 16 weights of models from our data, right? So that means we kept all the sheep in the gates, okay? And we don't have any data points outside the fences. And this means that we're okay. And to answer the question in the problem, in which states, are there any outliers, we would just conclude that therefore there are no outliers. And let's write a reason, okay? Let's say because no weights of the models are outside the fences. And it's really good to write a reason because, again, these are your notes. And so they're really for you to go back and refer, like, wait, why isn't it not an outlier? And what's with the fences? So if you write the reasoning behind it, then you can refer back and say, oh, yeah, that's why. Because it just, everything lies within the fences. Okay, so in order to determine percentiles, quartiles, and median, let's talk about relative frequency for a minute. Relative frequency were the proportion of the study in which had that certain category or a certain frequency for the study, right? And so when we found them, we found relative frequency and cumulative relative frequency, right? So we said here, and this is the number of cars per household. It was back in chapter 1. And we said, okay, 26% of the 50 households owned one car. Or we could say in the cumulative relative frequency, 78% owned 2 cars or less, because it was cumulative. And so the percentiles can be related to cumulative relative frequency. And in fact, these are exactly the percentiles. So whatever the cumulative relative frequency is at that data point is actually the percentile. So if I said here, what is the 78th and 34th percentile of the number of cars that households own, right? Well, the 78th percentile in the cumulative relative frequency, notice 0.78. This means 0.78 or 78% of the 50 households owned 2 cars or less. Where's the 34th percentile? Well, 34% is right above it, right? 0.34 of the 50 households, or in other words, 34% of the 50 households owned 1 car or less, right? That's cumulative frequency. So these values that you see in the cumulative frequency column are actually percentiles. And so we have here the 8th percentile, the 34th percentile, and the 78th percentile, and then 92nd percentile, and so on. And so the 34th percentile, the 34th percentile and the 78th percentile is going to be in the category of 1 and 2 cars. So where does the median lie? And you're like, what? I don't know. There's no 0.5 anywhere, right? Because that would be, the median is 0.5 or 50% or the 50th percentile. And if we look here, I don't see 0.5 anywhere, right? You're like, ooh. Well, it's kind of hidden. Because cumulative relative frequency says that 8% have 0 cars in their household. 34%, recall the line, recall the number line. Here's 0%, here's 100%. So 34 percentile is here, and that means 34% is here, and 66% is over here. Okay, so 34% does not contain the 50% marker, right? Because here's 50%. So which one would? Well, the next one is 2 cars household, which is 78th percentile. So let me do that like in green. So 78 is about here, right? That means that 78% lie below it and 22% lie above it. So which one contains 50%? Right? The 78. We couldn't do 34% because that doesn't include the 50% over here, right? The next category we had was 2 cars. So 2 cars had a cumulative relative frequency of 78%. So that did include everything 78% and below. It included 77, 75, 60, 55, 50. It included everything below. And since we were specifically looking for the median, we were looking for that 50% area, right? So this means, where does the median lie? Well, somewhere between the 34 and the 78. But since cars are discrete, we can't have like half a car, right? Don't laugh because I know some of you do. And so we just go by 1 car households, 2 car households, and 3 car households, right? Nothing in between. So this means that the median will have to lie here as well, because it includes the 50%. So let's write this out. Let's say something, right? So let's do the first part. So of the households, of the 50 households, that were sampled, 34% owned less than 1 car, 78% owned two cars or less, and 50% owned 2 cars or less. And so the second part we want to note is the median is where the 50% lies within the cumulative relative frequency column. So we can use the cumulative relative frequency and associate it with percentiles and see that even though the cumulative relative frequency gives us these random percentiles of our data, we can find our median or any other quartile. Like if I wanted to find the 25th percentile, where does that lie? Well, if I looked at 34%, notice that that would have had the 25% marker, and so that would have lied within 1 car household because the 0 car household only had a total of 8%. I could do 75%. We could see that the 75% or Q3 actually lies within 2 cars as well, because that contained 75% right here. So we can use the cumulative relative frequencies that we all did in chapter 1 and actually use it and apply it to this area in this section for quartiles and percentiles. Pretty cool, right? Okay, so then on this note, let's keep going with interpretation. So on a timed math test, the first quartile for the time it took to finish the exam was 35 minutes. Let's interpret this first quartile in the context of the situation. Well, you're like, okay, well, it's 35, 35% is below it, and 65% is above it. And we don't write that though. In statistics, we're trying to come up with meaningful conclusions, and they don't mean anything to anyone unless we write it in a way we can have a conversation about it. So let's conversate about it. Let's have a conversation of how long it took someone to finish this exam. Okay, well, this means that of the times it took students to finish the exam, 25% took less than. So again, the first quartile, before I move on, remember the first quartile is 25%, and the actual value, the Q1, is the data value from the study. So this would mean less than 35 minutes. And 75% took longer than 35 minutes. So again, we just really want to be able to interpret this in context of the problem. So if I want to take the information obtained from example 2.8 and interpret the median. So if you recall up here, example 2.8 was the models, right? When we revisited the 16 random selected weights of models. And we found that the median in this case was 110, also listed here in example 2.9. So the median is the 50th percentile, and which was 110. Now we know that these are models, these are weights of models, and the weight is in pounds. And we know that the median is 50% mark, which is halfway. So let's have a conversation about this, right? So of all the models' weights, half weighed less than 110 pounds, and the other half weighed more than 110 pounds. And so the median is very powerful. We use the median because it doesn't have any influences. And we're going to talk about that a little bit more when we compare the median and the average and those two statistical values. But the median is very powerful. We use it in different areas, and it actually can tell you more about your data set than the average. And so the average is always meaningful, but the median is pretty powerful in itself.